Okay, it's recording now. Okay, welcome to class, guys. I'm gonna continue with my recording last week I sent to you. So I'm gonna finish chapter 1.2. This chapter is about simple regression models, right? 1x, 1y, and then we talk about the concepts, right? What is the simple regression? How we can write it in a mathematical way in an equation? And then we talk about OLS. We use the OLS estimator to find the unknown parameters, right? And we need assumptions, right? 5 assumptions. We need the property. And then we talk about the variance of our estimator. Remember sigma square? And then the standard error. So let me continue with here. The final summary of chapter 1.2, what is it about? Okay, so as usual, I'm gonna draw a table. What is the concepts? And what is the key idea? The first one, what is simple regression? How we write a simple regression in an equation? It is y equal beta 0 plus beta 1 x plus mu, okay? And then we learned about OLS, right? Ordinary least squared. The key idea is that we want to minimize the sum of squared residual, right? Minimize the sum of squared residuals, okay? So here is residuals, okay? Be careful about the terminology. Residuals means hat, okay, after our estimation. Why we want to minimize? Because we want to find the baseline. And next one, the theorem, right? Unbiasedness. Unbiasedness just means the expectation or the expected value beta 1 hat and also beta 0 hat, but normally we care more about the slope, okay? Because here is the effect of x. So the expected value of beta 1 hat equal the true beta 1 equals the true 1. That means this is the unbiasedness, okay? But under which some assumptions, under simple linear regression, assumption 1 through 4, okay? We need those 4 assumptions in order to prove that the OLS estimator is unbiased. Next point, homoscedasticity. Homoscedasticity, I explained to you in the recording. Homo just means the same, right? Homoscedasticity, what does it mean? It means the variance of mu given x equals sigma square. Sigma square here is the constant term, okay? That means constant spread. Next one, after we talk about the variance of the mu, then we learned what is the variance of our estimator. So here I'm going to use beta hat as well. But you also need to know the variance of beta 0 hat, okay? I didn't show you the approve, okay? I think it's not necessary for you, but you just need to know the concept and get familiar with the equation. So for the variance of beta 1 hat is sigma square over SST from X, okay? So here actually sigma square here, this is how we get sigma square. This means if noisy goes up, noisy means the sigma square, right? Noisy means sigma square because noisy means that is the part that we can't explain. Y from mu, okay, means noise. If noisy goes up or noisy is worse, what will happen to our variance of beta 1? Okay, if noisy goes up, increase, our variance will worse. Okay, we'll have a bigger variance. Other side, let's think about the denominator, which is the variation in X, okay? Okay, here, the denominator here is the noise. And let me write it down and then I'll explain to you. Okay, guys, the variance you learned from statistics means the spread out of our estimate, okay? Of course, we want this one as smaller as possible, okay? Okay, so here, the formula for variance beta 1 hat is sigma square over SSTX. The numerator, the upper part, means the noise from the mu, okay? If the noise increase, of course, that means our variance of beta is worse. Because numerator increase, the whole gonna increase, right? And for the denominator, we have the variation in X. It means if you get more data, the variation in X will be increased. If the variation increase, if this term increase, our variance is less, right? Will decrease. That means the variance is better. And for OLS, it has the smallest variance, okay? Smallest variance among other linear estimators. That's why we call OLS is the best linear unbiased estimator. Linear just means we get it from the linear equation, right? But we have best. Best here actually means OLS variance has the smallest one. That means best, okay? Best linear unbiased. Unbiased means that one, right? The expected value of our estimate equal of the true. The true one means unbiased, okay? So best linear unbiased estimator. Blue in short term. Blue, okay? OLS is blue. Next one. After the variation, so we learned how to estimate because the noise, the sigma square here, this is from the true population, which is unknown. So how we estimate it, okay? And then we learned sigma squared hat. Hat means the estimate. How we estimate? We divide it by n minus 2, right? Why not n minus, why don't we just divide it n? Instead, we divide it by n minus 2. I showed you here, right? Here. Okay, here is the SSR, right? Here is the SSR. summation of squared residual, right? This is SAR. We use SSR divided by N. This is the first try. We want to get the estimate of sigma square, but this is biased. Why? Because we used beta 0 hat and beta 1 hat, which is two parameters. This is our degree of freedom, right? So we need to use n minus 2 instead of n in order to get the unbiased estimator for the variance. Okay, if we divide it by n minus 2, this means unbiased. And then if we get the variance, the next step is the standard error. Means how precise is our estimate. Let me help you with those symbols. Okay, so we have a sigma square. We have a sigma square hat. And then we have a standard deviation. And then we have standard error. So let's say we use S to represent the standard deviation. We use a sigma to represent the standard error. What is the difference for those four? If we talk about sigma square or the standard deviation, that means this is for the true population, okay? And the sigma square, we call it population variance, right? And if we square root sigma square, we get standard deviation, which is S, okay? So for population variance and standard deviation, those are for population. But for sigma square hat and the square root of sigma square hat, so we get standard error. This is our sample, from our sample. And sigma square hat called sampling variance. Okay, so when you write your economic exercise 309, and if you need to do the presentation about 308, you have to be able to read the estimation results, okay? So normally from a paper, they will show you, suppose the table here, they will show you two things. The first one is the estimation of our parameter, which is beta 1 hat. Let's see, okay? And next one, they will show you the standard error. Normally we use SE to represent, okay? Standard error SE. They will show you SE. Okay, so that means they will show you the standard error, okay? Normally it's 0.0. I couldn't remember the range of standard error. You may check by yourself, okay? So let's see. Normally they will show you this, okay? So you have to know that this one is the estimation parameter. This one is the standard error of that estimation parameter, okay? And standard errors tells us how much to trust our estimates, okay? How much to trust. Small SE, because SE is from the variance, right? We need smaller variance. So smaller SE, trustworthy. It means trustworthy, okay? It doesn't mean it's 100% true, okay? Because we are social science. So just like we can trust the estimation. And if it's large, means spread out, okay? If it's large SE, so you should be careful about that paper, okay? I didn't say it's wrong, okay? Just be careful. This is the bridge between estimation and inference, okay? What we do next chapter. So here we learned how to estimate beta 1. Next chapter we ask, can we trust that estimate? Is it statistically significant? That's where standard errors becomes our most important tool. Remember, I showed you here. No standard errors, no inference, and then no conclusions. Okay, so that's all about chapter 1.2. So now let me summarize. What is chapter 1 about? What we've done so far? Okay, let me draw the tree. Chapter 1.1, what is it about? It's about the concept, right? What is econometrics and how we distinguish different data types, right? The first one, we care about the causal and descriptive questions. And next one, data type. Right? Cross-sectional, time series, panel, or pooled cross-sectional. And then we said we have to explain it by ceteris paribus. Okay, so when you do your exercise, it's okay if you just answer 1x to explain the y that you are interested in. Okay, 1x to explain y. But you have to consider other important x, okay? Or you may get it from your theory, you may get it from the literature review. But this is your question, okay? This is the main question that you want to answer. But you also need to incorporate other x because those are control variables. If you don't have it, you may have omitted variable bias, okay? So this is about chapter 1. How about chapter 1.2? So we start with simple regression. One X, one Y. And then we need the assumptions, okay, for OLS. Assumption 1 through 5. And among those, the one that we care most is the zero conditional mean. And also homoscedasticity. Based on the assumptions, we have the unbiasedness. And the variance of beta. So beta here in general means our two parameters, right? Beta 0 hat, beta 1 hat. And then we use sigma square over SST. Okay. Which means, is there more noise or you have more signal from your data? And then the error variance, which is sigma square hat equal SSR, the summation of mu residual squared over n minus 2. Okay, we divide it by n minus 2 because we need degrees of freedom correction. Okay, this is what we've learned so far. So next chapter, we're gonna learn multiple regression, means many x, but one y. If you want to incorporate many x to explain your y, how many x do you need, right? What is the most important? What is the priority? You must have the priority of x. Like if you want to explain the consumption, the quantity, we're gonna use the price, of course, right? Based on the law of demand. How about other factors, right? The income, the relative goods, right? Those kind of x. So we're gonna talk about how we explain, if you just want to explain one x, and how to find those x. So how many x do we need in order to explain that y? How many is enough? Okay, so let me go through a quick roadmap about chapter 1. The first one, what is econometrics, right? The goal, estimate relationships. We want to test theories, forecast, evaluate policy. So we need econometric model, and then we're gonna have our economic models, okay? I remind you that for economic model, you need to choose it based on the theory or literature. And then we have data types, right? Cross-sectional, time series, pooled, cross-sectional, and panel. And then how we interpret causality, we use ceteris paribus, means all else held fixed, okay? The idea is from randomized experiment. Okay, those are the types of different data, how to differentiate, but I'm not gonna go through here. So here, most interesting economic questions, return to education. I showed you effect of police on crime, minimum wage and unemployment are ceteris paribus or causal questions, but real data is rarely from a controlled experiment. So co-founding factors are a constant concern. Co-founding factors means many X, right? We have co-founding factors, right? Many X, okay? And next one, the simple regression model we just finished. Here is the equation. Okay, what is y, what is x? Beta 0 means intercept, beta 1 means slope, u means error. And we need this assumption, zero conditional means, right? This is very important. Because of this zero conditional mean, and then we're gonna see that the population regression mean is as follows, okay? And then how we estimate OLS, we want to minimize sum of squared residuals, okay? And then we use OLS formula to find beta 1 hat and beta 0 hat. Y hat means the fitted value because it was hat, and mu hat means the residual equals the true Y minus the fitted Y. About the interpretation, okay, holding mu fixed. And then we talk about R squared, how to calculate, right? We use SSE over SST, means the share of variation explained by X, okay? How many X can explain Y? This is how R squared means. But it doesn't mean causality, okay? It doesn't mean causality. Okay, we have the algebraic properties of LLS, right? This is properties, not assumption. It always true at any sample. The first one, residuals sum to 0. Second one, X is uncorrelated with the residuals, okay? They must be uncorrelated. And then the regression line passes through the point of the means, okay? Y bar, X bar, those are the means, okay? The average. And then the total variation equals the explained part plus unexplained part, okay, which is the residual variation. And then we have our three functional forms, right? The first one, level just means from statistics, just means original. We didn't do any transformation for our X and Y, so we call it level. So here means Y, X. So level means here, Y is level, X is in level. So here is the equation. You should be very familiar with it now. And how to interpret? It means 1 unit increase in X will causes beta 1 unit change in Y, okay? About the change, if it's positive, if the sign is positive, so they have a same relationship, positive relationship. If the sign is negative, that means X and Y has a negative relationship, right? Next one is semi-log, which means we take log only for Y, but not for X, okay? We call it semi-log, log level. Here is the form and how to interpret. Because interpretation is very important for you guys, okay? You have to present your exercise after you finish. So you need to interpret what is your beta 1 hat, okay? Here, 1 unit in Y increases because we have X as level. Will causes 100%, 100 times beta 1% change in Y, okay? So X is 1 unit, but Y here is percentage. The next one, log. So here we take log, and remember it's natural logarithmic for both Y and X. And then we have the form here. The interpretation change as well. So here means 1% in increase in X will cause how many beta 1% change in Y. And here, from microeconomics, we call this one elasticity, right? Remember the price elasticity? And I explained to you why economists normally we love log model. Okay, so if you see some academic paper, so they may show you that log Y equal beta 0 plus beta 1 log x plus mu. Okay, you may say in this form. This just means that the log here is natural log. Do you still remember what is the reason why we take log? Still remember? Percentage change, okay. Okay, so here I want to emphasize xy is your data. So you barely use your original data to run the regression because it fluctuates a lot. It has a trend, right? So first so for the transformation, the first one, we can use the electron log transformation. So this can reduce the variation for your data, okay? Another point why we use log, because sometimes we have data is negative value, 0 or negative, but you cannot take log for 0. Sometimes it's negative. So we take log to make it become non-negative. So it will have a concave function. It always goes up, right? So this is the reason why we take log. After you take log, you have to check, especially for time series, you have to check the data, is it stationary or not? If your data is still not stationary, after you take log, so you can take the differentiate, first differentiate, okay? In that case, if you take differentiate, you need to take differentiate on both x and y and for all your data sets. So we can have an easy explanation, like how we explain differentiate in economics. How we explain differentiate in economics? Growth rate, right? Growth rate. If we use the differentiate. And then the 5 assumptions, right? The first one, SLR means simple linear regression. The first one, linear in parameters, okay? This is linear in parameters. The second assumption, random sampling, right? We talk about this many times, especially when you collect your experimental data. You have to make sure that the method that you collect is random sampled, okay? Otherwise, nobody gonna trust your data. So here is our data, xi and yi is an IID draw from the population. What is IID? Have you heard about this one? This is a very important assumption, okay? What is IID? It means independent and identical distributed random variables. They have to be independent, right? And identical distributed random variables. IID means independent and identically distributed random variables. Next assumption, sample variance in X. X is not consistent across observations. Try to get more data as possible. And assumption 4, zero conditional mean. Zero conditional mean means mu and X, the expectation equals 0. Okay, under assumption 1 through 4, OLS is unbiased. Okay, this is our theorem 2.1. And the last assumption, homoscedasticity, which means the variance of mu given x equals sigma square. Sigma square is a constant, even it's unknown, but it's constant, okay? This is a good thing. So this means homoscedasticity. And then we can get the sample variance formulas through our theorem 2.2 for beta 0 hat and beta 1 hat. So here, right, assumption 1, 2, 4, OLS is unbiased. If we add assumption 5, we can derive variance beta 1 hat equals sigma square over SSTX and estimate sigma square unbiasedly with sigma square hat equal SSR over n minus 2. I emphasized this so many times. And this is our theorem 2.3, given us stand errors, okay? Stand errors is the one that you need to report in your paper. Hmm? This means that your data, your data that you get from your experimental, you collect it from, or you get it from some data website. Okay, they must. So like this is x1, x1, y1, x1, x2, y2. They should be independent. They should be not related to each other. Like he make decision based on his own, and his decision doesn't affect yours. This means independent. Okay. The identical normally we use it to describe the normal distribution. Identical. Okay, so your data should normally we assume that because we don't know what is the real distribution of our data. So we assume that our data is normal distribution. And for normal distribution, it follows IID. Okay, so this is the simplest way to explain or to use for you and for me as well. We assume normal distribution all the time. Because of what? Remember you learned from statistics, there is one law. Why, if we randomly sampled our data many times, finally it will has a normal distribution. Central limit theorem, right? Because of central limit theorem. I hope it's helpful. Okay, so let's see the big picture. Chapter 1, set up why we regress, okay? We win the causal ceteris paribus questions using non-experimental data. Okay, so for you guys, about your 409, what kind of data do you want to use? Experimental? You're gonna go and collect by yourself? What do you think? I think this is one difference between economics and social science. Okay? The department just opposite us. We normally use non-experimental data. That means we download the data from the stock market, from the data website. Okay? You have to know what kind of data website that you use. CESA database or other than you have to pay. But for CESA database, you can search. If you use a same use IP to access, it's free for you. Okay? You just visit as a guest. But for social science, as far as I know, I have many some friends they study there. So they study about like the ethnic group, human rights, the environmental something. Normally, they get their data by collecting the survey themselves, which is quite tough. Okay, you should have a team to do that. You should have money. You should have people that. What's your design? Applied econometrics. Well, it's useful. When I first learned econometrics, like when was that at your age now? I couldn't understand at all. I'm not sure about you guys. And you know, finally about my grade, I got state plus for econometrics. Okay. Oh yeah. Because I continued my study and it's useful. You will see it. Because it's about quantitative analysis, okay? It's about quantitative analysis. I don't like qualitative. You need to know what is that. Then for your paper, or it's about words. I like some equations, okay? So for social science, they're gonna use experimental data. But of course, we have the pros and cons about each data set, right? For ours, non-experimental, you can get it free. That means everyone can get it. Okay, so you don't have any, it's not private, it's public. So everyone can use it. If you guys use the same question, the same data, and then you're gonna have the same paper. But if you use different estimation method, you're gonna have different results. Okay. But for experimental data, that means they go and collect by themselves. So it's private. It's quite free precious, right? So think about it. What kind of data you're gonna use for your research? And don't worry, you guys will be fine. Even I get C+, but now I'm here to teach you guys. And another suggestion is that I told you that yes. Are you very good at mathematics? No, I'm not very mathematics. Sometimes like only the people who are good at mathematics should choose. Econometrics needs math and statistics, right? But for math, we only use it like to find prime orders, like I showed you. Actually, the math that we used in econometrics is not difficult, like first order conditions, city equal to 0, you can find the result. It's not that difficult. But maybe at my level, I'm not sure about the other. But if you take the finance econometrics, if you go to the top and if you study in deep, you will find that it's all about mathematical proof. Okay. It's not, I'm not very good at all. But the knowledge that I have is enough to help me solve the estimator that I want to find. And later, if we do the lab, you will understand that you need the formula from mathematics to run the code. And if you're good at mathematics, actually you can coding by yourself. I have one friend. She's a mathematician, but right now she's teaching at camp about software engineering. Okay. Okay. Another suggestion for you guys. Here I told you we want to use one y to expand y, but this is not practical in the reality. Okay. So you must find many x to expand y. But right now, a lot of paper already done about the factors that we want to use to expand y. So one suggestion from my side, you may consider the asymmetric effect of y. What does it mean? So in economics, we have a recession, we have a, what is the next one? Recession and the business cycle. Recession and, I forgot the word before. Boom and recession. Yes, boom. Okay, we have boom and recession. So people's reaction might be different during boom and also recession. This is what I'm doing for my paper, okay? I investigate the asymmetry. Or you can also think about something, suppose the price, okay? We have price. If the price increase, what will affect people's assumption? If the price decrease, what will affect people's assumption? This is also called asymmetric and non-linear, right? Because it's not one line. They will have a negative, positive. Okay, think about it because it's easy to find the research gap. Otherwise, if you want to find, what I mean is that right now many X already be found that have a relationship with Y. That is. So think about it. Okay, so let's continue. Chapter 1.2 gives the simplest possible tool, which is one regressor, to estimate such a relationship, together with the conditions under which OLS is trustworthy. How we say it's trustworthy, we check the unbiased and with homoscedasticity, we has known sampling variance. Chapters ahead, relax the one regressor, okay? Like next chapter, we're gonna learn multiple regression. That means it's not only one regressor, okay? To multiple regression, so we can make ceteris paribus more credible by explicitly controlling for more factors. Okay, that's the summary from my side. Do you have any question about chapter 1? Because on Thursday, I'm gonna go through to chapter 2, which is multiple regression. Now? No, because the quiz is about chapter 1.
But it's my first class here because I've been absent for the past 2
But you should consider about your other friends as well.
They would enjoy a quiz on Thursday.
No. It's better do it here. Have you reviewed my recording? Okay, so I think I'm done from my lecture, but no, I haven't finished, okay? So get your app, get your phone down. We're gonna do the quiz now.